Okay, so in the notation that we've been using, okay, the expectation value is first you take the operator, okay, and I'll explain that in just a second. First you take the operator Q hat. So Q hat is the operator that corresponds to the observable Q. So Q without the hat is a quantity. It's a measurable quantity or an observable, okay? And Q hat is the operator associated with that observable quantity, that measurable quantity. So first you take the operator, you operate on the wave function psi sub x, then you take the inner product of that with the complex conjugate of the wave function, you integrate that over all space, and you get and that gives you the expectation value. So this is very much like how we defined over here the average value of a particular quantity. In this case, the energy. It's the probability of getting that energy times the energy, and then you sum over all states. Here, um, we have the probability density psi star psi sub x. If the q wasn't there and we basically integrate that over all space, that's psi star psi is the probability density. So we integrate that over all space. That's the probability. Um, and but what we do here in quantum mechanics is that we have to insert this operator here, which somehow corresponds to the quantity that we're trying to measure. So here we basically just multiply the probability density times this value. Here we basically have to insert this operator between psi star and psi. Okay, and it's important for reasons that we'll understand as we continue on in the class. Okay. Again, psi of x is some arbitrary superposition state. So I've changed my notation from f of x to psi of x because this is just what's traditionally used in quantum mechanics. Again, it's the superposition of these basis states, the eigenfunction the psi sub n's. Okay, and here I'm assuming a one-dimensional geometry so that we're only have to integrate over one dimension. Okay, so again, this q hat is the operator corresponding to a particular observable, and examples of operators. So if we want to measure the average position of a associated with our wave function, okay, so we make a measurement of the position of our particle. Our particle is described by a wave function. We make a measurement of the position at a particular time, okay, and we're going to get back again a number. We're going to get back a number that corresponds to its position. We can't get back a range of numbers. Again, to the precision of our instrumentation and of our experiment, we have to get back a number, okay, and so the operator associated with the position, the measurement of the position, is just the position. Okay, so it's essentially trivial, and can be x, y, or z, just depending on the geometry of your problem and what you're interested in asking. The momentum operator, as it turns out, and we won't justify this here, is actually, and this is now we see why it's an operator, is that this actually involves a partial derivative. So the x component, the x momentum component operator is equal to minus I h bar d by dx, and similar for the y and z components. Okay, so now you might see, now this acts on a wave function. Okay, so when you basically put this in front of a wave function, then it acts on the wave function. You'll be taking the derivative of the wave function. The energy operator is actually one that we've already mentioned a few lectures ago, which it's called the Hamiltonian operator. We denote it typically by h hat or h, and it's just minus h bar squared over 2m times the Laplacian operator, or d squared by dx squared plus d squared by dy squared plus d squared by dz squared. Remember, the Hamiltonian operator is just del dot del. Okay, del isn't I'm not defining it here, but you should know what the del operator is, and plus u of x, where u of xyz, where u is the potential energy term. Okay, so again, this is the Hamiltonian or the energy operator.